welcome to Sunday's edition of Cracking the Cryptic, and a very happy Easter to you all. Now, today's puzzle is by Lizzie01. Lizzie, who's appeared on the channel once before. I think Mark did one of her puzzles around the time of the Tartar Steel chess tournament. And Lizzie's puzzle was all about chess in that instance. Well, this one isn't. Lizzie emailed this one to us and says that she thinks it's her best and hardest puzzle, and she'd like to see me have a go at it. Well, I'm going to do just that, although I have had a sneak preview of the rules, and it's disjoint subsets, which always makes a little part of me die a little bit. Not because I don't actually enjoy the rule set. I do like the rule set. I'm just so conscious of the fact that it's really easy to miss easy points with that rule set, and that tends to make me feel a bit daft when people are watching me solve using that rule set. So wish me luck. This one could be a long one, I think. Before we get started, a couple of things to mention. Obviously, if you own our Thermo Sudoku app, I mentioned this the last couple of days, there's a big update now. There's 20 new puzzles. I'm already hearing some really nice comments about those new puzzles, so check them out. Just make sure your app's updated, and those puzzles should be available. And of course, over on Patreon, we've got DiMono's sequel to Everything Is Wrogn. That is up there, and that's also been getting some great comments, so check that out too. Apart from that, nothing else to tell you, so I shall read the rules. We have got normal Sudoku rules apply, that's good. Digits in the same position relative to their box must be different. So this is the old disjoint subset rule. So what this means is that if this square here was a 1, for example, then in every single topped left position within a 3x3 box, you couldn't see a 1 in any of these squares, because there's already been a 1 in the top left corner of a 3x3 box. Now, in effect, what this means, of course, is that these yellow cells I've just highlighted there have to be a complete set of the digits 1 to 9. And that's why it's called sort of disjoint subsets, because effectively in this puzzle, you don't just have to make sure that these 9 cells here contain the digits 1 to 9, and these cells, the rows, contain the digits 1 to 9, and the columns contain the digits 1 to 9. You've also got to make sure that all of these disjoint groups also contain one instance each of the digits 1 to 9, which is, yeah, it's interesting. Now, what else? We've got the main diagonals. The main marked diagonals contain no repeated digits. So again, that's another disjoint set in effect, because we've got to make sure that those yellow cells there are one complete set of the digits 1 to 9, and the same on the other blue diagonal. And then clues outside the grid indicate the sum of all digits along the indicated diagonal. Digits may repeat along these diagonals if this wouldn't conflict with the other constraints. So let's pick an example. 22 here. That means these squares along the arrow, so those 7 cells have to add up to 22. And it's fine to repeat a digit, but not so you break the rules of Sudoku. So what you can't do is that. That's patently wrong. That's going to give you a big problem in box 6, but it would be fine, for example, to do that. That doesn't seem to break any of the rules. So you can do that if you want to. Do have a go. The way to play, of course, is to click the link under the video as usual. Now I get to play. Let's get cracking. Now, the testing reports say that this is a very clever and very difficult puzzle. So I could be in for a long one. I've got 15 diagonal there. So that's got to be either 6-9 or 7-8. Why don't I pencil that in to make myself feel like I'm making progress? Now, of course, we may have to use the secret here. So the secret is that these yellow cells I've just highlighted, we know in the finished solution there will be one instance of the digits 1 to 9. So we'll have all of the digits from 1 to 9 in box 7 of the grid. Add up the digits 1 to 9, you get 45. Now, if we look at this box carefully, look, those cells must add up to 12 plus 15, so that's 27. 27 plus 4 is 31, so these 3 squares add up to 14 to get us to our 45 total, and that is completely useless. 8 diagonal, So 3 cells that sum to 8 must include a 1. It's 1, 3, 4 or 1, 2, 5. 2017. Oh, 42 in 5 cells. Ah, okay. Now that's incredibly constrained. Right, okay. This might be where we're meant to start. Because we've got the absolute maximum I can make those 4 cells add up to is 34. And that would be if I put an 8-9 pair here and an 8-9 pair there. So this little square has to be at least equal to 8. So this is an 8 or a 9, and whatever it is going to fix the nature of the 15 diagonal. Oh, right, okay, now I see what's happening. We can use the disjoint subset rule straight away. Very nice, this. Let's imagine that these 4 squares here were each a set of the digits 8 and 9. So we have an 8, 9 here and an 8, 9 here. Well, because of the disjoint subset rule, what you can't do is this. Because these 9s are in the same position in their boxes. So these 9s clash through the medium of madness that we're having to employ to solve the puzzles like this. So what if you get 8 9s in the same positions within their boxes like we'd have here? They have to be sort of offset. So that you can see the 9 here and the 8 here are in the same position. The 8 here is in the same position as the 9. Now, if this was indeed the arrangement, how could we make the 15 diagonal work? There would be no way. These are in the same positions in their boxes as these 8 9s. So you couldn't put an 8 or a 9 in either of those squares, which would mean the highest value you could put into them would be a 7 and 6 pair. 7 and 6, here is a knowledge bomb, don't add up to 15. So you can't have 8s and 9s in these squares here. And if you can't have 8s and 9s, this is going to have to be a 9, because we need to make sure that we can get to the 42 total. And we've only got 1 degree of freedom, in effect, along this diagonal. So you're going to have a 9-7 pair and a 9-8 pair in these squares, because 9-8, 9-8 is not possible. And of course 9-8 plus 9-7 is 33, and that means we need a 9 to get up to 42. Now the 9 here is beautiful, because that means we get a 7-8 pair to make the 15 work. Now I'm tempted to use my secret again. Let's use the secret again now, because the 9 here is going to have quite a prodigious effect, I think. So we had 27, yeah. So now these squares add up to 40 using these 2 little diagonals and the 4 and the 9 pair, which means these 2 squares have to add up to 5 to get us to 45, and we can't use 4 in the sum. So that's a 2-3 pair, which means these squares have got to be 1, 5 and 6 to complete the box. And we have a start, and so far it's been clever but not impossible. Now, how do we keep this going? We know there's a 9 in each of these sort of cells, because we know that one of these is a 9-8 pair, one of them is a 9-7 pair. 41 diagonal. 41 in 6 cells. That's a little bit restricted actually, because you can't use 9 in these 3 cells, look. And you can't use 8 and 7 in these 3 squares. So the highest these 3 squares could be would be 8, 6, 5, which is 19. Which means these 3 squares have to add up to at least 22 to get us to 41. And the one thing I know about 3 cells that add up to 22, if you can't repeat a digit, is that they have a 9 in them. So this is... well, the other thing we can say is that if these have to add up to at least 22, they must be at least equal to 5 individually, because this is, even if it was 22, you can't then use a 4 in the sum, because then you'd need double 9 in the other 2 digits. Right. So let's just come back here. If we know the highest this can be is 24, if this was 7, 8 and 9, so the lowest this can be is 17, and the highest it can be is 19. So there isn't a lot of freedom along this diagonal. Don't know whether yeah, have we got, if you think about the digits 7, 8 and 9 in these positions and these positions, these are like triples, aren't they? So in the bottom middle position within the 3x3 box, sort of position 8, this position, we know we've found a 7, 8, 9 triple in these 3 squares here. And the same is true of position 4, I'll call it, you know, this square. Those squares must be a 7, 8, 9 triple. So that means in all of the positions, in all of these positions across the whole grid, you can't have 7s, 8s and 9s. Okay, sorry, no, that doesn't seem to do anything, does it? Okay, what do we do next? Can we do better along this diagonal? This diagonal looks like it is at least a bit restrained. If you had what would happen if you had no 8 and no 7 in here? Would it then it couldn't work. 6, 5 and 4 is only 15. That would make those have to add up to 26. So we know that whatever these 2 squares are, the other of the triple, the other 7, 8, it's not 9. We know the 9's in one of those. So the digit that's 7 and 8 in this box that is not in this pair is on this diagonal. Let's mark that in case, hopefully I'll remember what that means. Okay. Sorry about this. I'm not exactly seeing what we've got to do here. 22 in 7 cells, so the average is very close to 3. I'm not seeing any restriction on low digits. I'm not really seeing many restrictions on high digits. What's the lowest we could make this add up to? You could put 1 there, 1, 2 there. That's not affecting any disjoint sets, so we're up to 4. Oh, that's a thought actually. Look, those 3 squares are all in the same disjoint set. They're all in the top right corner of their box. So the minimum these can be would be a 1, 2, 3 triple. So that's 6. 6 and 3 is 9. Put a 1 here, that's 10. You can't then put a 1 there because that's in the same position as this, but you could put a 1 there. So 1 and 2, 13, 9 degrees of freedom to make 22. That is not where we start. 20 here. 20 here would almost be interesting if these 7s, 8s and 9s affected this total somehow, but they don't. 17. 17 in 6 cells. Can't use 3 in this one, so that could be 1, 2, 4, 7. 7. Is there any reason that can't be 1, 2 and 3? I don't think so. So that's 7 and 6 is 13, so there's 4 degrees of freedom along there. Good grief, okay. 9 maybe in box 9. I'm just thinking I can't put 9 on the 8 diagonal. Ah, yeah, okay. 9 is a little bit restricted in box 9 because you can't put 9 in those two squares because of the disjoint subset. We know that we've already looked at this, but these two positions definitely have 9s in them in these boxes. So we can't go and put more 9s into these two positions in other boxes. So 9, let's just check this. 9 has to be in one of 2 places in box 9. It's not. 9 is not here, therefore. Okay. 9 in box 3. That's actually really interesting. That is incredibly surprising. But look, we've got the same 2 cells from these disjoint subsets being useful in box 3. Those 2 squares can't be 9s. So you can lock 9s into one of 2 places there as well. Let's see if we can keep this going. Yes, 9s in this box. Same point happens. Right. Now what I've noticed is that those 2 9s are in the same positions as those 2 9s. So between these 2, we might as well colour these, you can't have 9s now in either of these 2 positions in any of the other boxes. So in fact, let's colour them. Colour more 9s in. So in box 5, you can't put 9s. Ah, that's not useful. Bobbins. What would be useful is if I knew where the 9 was on the diagonal. 9 in this box. Can't go in those square. Good. This is amazing. 9 in box 2 is also restricted by this 9 pair, these 9s, and these 9s. And 9 is in one of 2 positions in box 2. So now maybe we can do better. Yes, we can. We can do better in box 5 now. These 2 can't be 9s because of the greens. 9s are in one of... Now I've got 9s aligning in these boxes. And oh, I see. So I've got like a complete set of 9s, like pairs of 9s that are possible around the grid. Surely we can get rid of one of these possibilities. Most likely is that we're going to be able to use the diagonal to get rid of one of these. Can we get rid of it easily? Can I visualize it? We can. 9, 9. Oh, actually it's very simple. Yeah, this can't be a 9. That cannot be a 9. Because think about what happens if this is a 9 to the purple group. Now there has to be a 9 here because of the diagonal. And in terms of the blue group, there has to be a 9 here because of the diagonal. But now look, in the blue group here, the top position has been used up by this 9. So that forces a 9 here, which clashes. And therefore, I think that's going to resolve everything about 9s, because now we know that the 9 is not on the diagonal in the red. So this is 9, which fixes the 9 in the other red, which fixes the 9 in the purple, which fixes the 9 in the other purple, which fixes the 9 in the blue, and the other blue, and this one, and therefore this one. And we've done all the 9s. Just like that, all the 9s have done. That's lovely, surprising, and clever, and difficult. it's all of those things. But now we can at least make progress again. So get rid of the 9s from here. Get rid of the 9s pencil marks there. 7, 8. 7, 8 pair in row 9. That's not a 7 or an 8. So that diagonal. Can't remember what we said the numbers were for this diagonal. I remember 22 was a number there, wasn't it? I think 22 is the minimum we could put in that diagonal. Yeah, okay, so this has to be at least equal to 17 if that's 24. And there's a weird virtual 7, 8 pair involving these 3 squares. Oh, so there's a 7, 8 pair in column 1 as well. Oh, well, I'm never one to refuse. In fact, I'm going to colour that, but I'm just noticing those awkward 9 pencil marks that I don't like the look of. So I'm going to get rid of those first. Get rid of those, get rid of the 9 from there. Come back here. Look at these 7s and 8s. I can colour them. So we should do that. And now we know purple is in one of those 3 cells, which I don't think we know how to do that. Green is in one of these 3 cells. That feels very symmetric, doesn't it? So suppose whichever one of these is the 7 or the 8 in box 8 is purple, actually. Does that matter? Maybe I should label it just to make sure that I've got it in my head. Does that matter with this purple? No, I don't think it does. Okay, so how do I've got these 9s, these lovely 9s that I had to work very hard for. Now what do we do next? We've got 11 here to complete the 20 diagonal. No. Okay. 17 here. I've already looked at the 17. It didn't do anything. Especially not as it feels like the restrictions at the top end of the digits, doesn't it? It feels like we know a little bit about 7s and 8s and a lot about 9s. So I don't feel I know very much at all about sort of the 1, 2, 3 side of the equation. We know that these squares have to be relatively low. Oh dear, I've come to an absolute cul-de-sac. What on earth do I do here? It's about now that I sometimes wonder if I've not, if a clue's been missed off or something like that. Because none of these diagonals seem to be very useful. Maybe I'll highlight them all and see if that makes me think of anything. I'm not highlighting that one. I've done that one. I'll highlight this one. This one. There's a single overlapping square here between the 8 and the 22 diagonal. But other than that, it looks like they're almost being designed to miss one another. Does that look familiar to anybody out there? Right. Can we... Is there something going on, I'm wondering, between the 22 and the 17 somehow? These seem to have to be low on average. The 22 has an average value of around 3. 17 has an average value of just under 3. No, 1, 2, 4, 5. 2, 4, 5, 1, 2, 3. Yeah, so I mean, things like this. I mean, there's no particular reason this has to be a 1, because there are 9 degrees of freedom on the 22 diagonal. But if this was a 1, then what would be the minimum you could make those 3 squares? They'd be 2, 4, 5, which is 11. 11 plus 1 plus 2 plus 3 is 17. So if this was a 1, you would all of a sudden know this diagonal, or at least you'd know an awful lot about it. But unfortunately, there's actually no reason this can't be an 8, I think. That's an interesting thought. Right, okay, here is a thought that is it right? I think it is right. I think it is right. One of these, see this triple here? See this triple here. Is it possible both of those sets of 3 contain a 1? And the answer is I don't think it is possible. Because we know there's a 1 somewhere on this diagonal. I don't know where it is, but wherever it is, let's imagine it's there, just for the sake of exposition. Now we know that the top right cell of all boxes cannot contain a 1, so we would not be able to put a 1 in any of those 3 cells. Now, on the 8 diagonal, I know there's a 1 in one of these 3 cells, so let's pick another of these cells and say that, so let's imagine the 8 had a 1 here. Now that would mean that the bottom left cell in all the other boxes couldn't contain a 1, so those 2 squares couldn't be a 1. And now, I can't put 1s in both of those squares because they will clash. So, if you like, because we know there's a 1 on the lead diagonal, or this diagonal, I don't know if it's some people call them different things, but this diagonal here must have a 1 on it. This diagonal must have a 1 on it. You can put a 1 on one of these sets of 3 squares, but not both. And that means one of these sets of 3 squares along the 17 diagonal, either this box or this box, will have a minimum value of 2 plus 3 plus 4. So in fact, if this one doesn't have the 1 on it, we would all of a sudden know the 17 diagonal. But if that one does have a 1 on it, and this one was 2, 3, and 4, that would be 9. These would have to add up to 8. There's something going on here. I can't quite get my head around it, but it feels very important that along the 17 diagonal I can only include 1, 1. I suppose what that might make me ask is whether you can have That's interesting as well. You can only have 1, 3 along this 17 diagonal. I could put a 3 in one of those, but I can't put a 3 in one of those. So maybe the question we have to ask is about 2s. Is it possible that this 17 diagonal has only 1 2 on it? Obviously I could put a 2 in there and I could put a 2 in there. That doesn't break the rules of Little Killer and would seem quite a sensible thing to do. But let's try and not do that. If there is not 2 2s, then this diagonal could have a maximum of 1 1 on it, a maximum of 1 2 on it, a maximum of 1 3 on it, and then it could have 2 4. So 1 plus 2 plus 3 is 6. It could have 2 4s on it. That breaks. 2 4s is already 14, and the next digit I can use is a 5, which takes us to 19 and breaks the total of 17. So this diagonal has 2 2s on it, and that feels interesting. So it's got 2 2s and a 1, and a maximum of 1... Sorry, I'm going to have to do this slowly. It's got 1 1 on it as a maximum. It's got 2 2s on it, we know that, so that's 5. It's got a maximum of 1 3, so that's 8. And I've used up 4 digits now, and I've got 2 more digits to use, and I can't use any more 1s, 2s and 3s, so the only way of getting to 17 is with a 4 and a 5. So it's this diagonal, we've actually worked out what it is. We might not know the order, but it contains 1 1, 2 2s, a 3, a 4 and a 5, and there's no 3 in there, and there's definitely a 2 in both sets, so there's definitely a 3 in this one because we need a 3 and it can't go in this one. Oh, and I tell you what, there's 2 2s on this diagonal, so there's a 2 in that set and a 2 in that set. That's going to use up 2 of the positions of 2s in this diagonal's disjoint subset. And this diagonal will use up the 3rd position for 2s, because there must be a 2 on this diagonal. That means you can't have another 2. If we were to try and put a 2, for example, in there, we've run out of ways to do this now. We now know we'd have to put a 2, say, in that position there. That forces the 2 in this box here, because you can't repeat in the middle. You can't repeat in the top right. And now you can't put a 2 on this diagonal, because there's nowhere for it to go. Bottom left is ruled out. Middle is ruled out. Top right is ruled out. That means that this diagonal is 1 3 4. And we can do that. That's not 4. Oh, whoopsie, that's not 4. Now, what does that mean? It's not actually very useful for that square, is it? What I want is to get some high digits on this diagonal. Doesn't seem to do anything at all. Golly, that was a lot of logic for nothing at all. What? There's a 1, 2 2s, a 3, a 4 and a 5. Ah, yeah, okay. Okay, I see. I see. Am I meant to combine this with this one? And this one, probably. Let's have a think about this. So now, if we were to consider all 3 of these diagonals and work out what digits are now used up. 1s are used up. There's a 1 here, there's a 1 here, and there's a 1 here. 1s are used up. 2s are used up. There's a 2 here, a 2 here, and a 2 here. 3s are used up. There's a 3 here, 1. There's a 3 here, 2, and there's a 3 here, 3. 3s are gone. 4s, 4 here. 4s are used up as well. 1 here, 1 here, and 1 on the diagonal. 4s are used up. 5s. 5s are not used up. There is a 5 on this 17 diagonal. There will be a 5 on this diagonal. But there can be another 5. In fact, there must be another 5. So what have we learned from this? We've learned we can't put 1s, 2s, 3s and 4s in these positions. I wasn't planning on putting them in those positions anyway, or those positions, that's it. You can't put 1s, 2s, 3s and 4s there. Does that rule out something from this side of this? I'm wondering now whether we know more than we did about these 3 squares, if you can't use a 4 in the total. Because we know one of these squares is an 8 or a 7. So if we were to have 3 here, 3, 8 plus 6 is 17. That feels like it might work. Oh no, we can't use 3, because I can't use 3 either. Oh, in fact, maybe that's the point. If the minimum I can put in there is 5, and I can't use 7 and 8, then this has got to be either 5, 6, 7 or 5, 6, 8. That's the only things it can be. So I see. So it's a triple, well, a quadruple, in fact, using this square. So these squares are made up of 5, 6, 7 and 8. That one is not 7 and 8. But I can only use one of 7 and 8 here. So I must use 5 and 6 on this diagonal. Right, sorry, I'm being a bit slow, but I hope you'll forgive me. This is pretty interesting stuff. So we've either got 11 plus 7, which is 18, or we've got 11 plus 8, which is 19. Which means this is either adding to 23 or to 22. Okay. Ah, yes, but, yes. Is it possible this triple doesn't have a 5 in it? The answer is no. If this doesn't have a 5 in it, how would I make this triple work? I can't use 6, 7 and 8, and I'm not allowed to use the digits 1, 2, 3 and 4 in this diagonal anymore. So there would be no way of making the diagonal work. So there is a 5 in these 3 squares, and therefore count the 5s. We've used a 5 in one of those 3. We've used a 5 along the 17 diagonal. We've used a 5 in the main diagonal. So there can't be any more 5s up there. There are no 5s up here. So if this is adding to 22, this is 6 and 7. And if it's adding up to 23, it's 6 and 8. Okay, so there's always a 6 in here. And was there always a 6 in here as well? There was, wasn't there? There is. There's always a 6 in here. So this, the 41 diagonal now, we have worked out, contains 2 6s. So now, with that diagonal, that's all the 6s used. So now, oh, this is just gorgeous. That is one of the most beautifully executed ideas I have ever seen in Sudoku. That's a 7-8 pair. Let me just check that. That is my gut instinct, is that this is a 7-8 pair. And that's because these diagonals now, I'm going to highlight all of them. We have proved all of these diagonals they definitely contain 1s, 2s, 3s, 4s. They contain 5s. This 1, 2, 3. They contain sixes. 1, 2, 3. So the only options for these squares, it can't be 9, they've got to be 7 and 8. They can't be 1, 2, 3, 4, 5 and 6. This is a 7, 8 pair, which I can colour. Good grief. I mean, this puzzle, I mean, it's actually really surprised me. I have to say that. I thought when we started it, it was a nice idea with the 42 leading into the 7, 8, but I had no idea that this was going to become, you know, this intricate. Now, so there's got to be green in one of those. It's got to be, yes, look. Yes, there's got to be a green in one of these by SUDOKU, and then we've got a green on this diagonal. That is green. Now, can we keep this going? Not sure. Do we know, actually, do we know what colour? We know there's a 7 or an 8 on this diagonal. I'm just wondering if I know the colour of it. I do know the colour of it. In fact, let's actually think about purple. Purple in the top right of its box has been used up by this purple. This square cannot be purple. So this square is a 5 or a 6. This square, therefore, is the only square left that can be purple. And this is, so this is not purple. So this is purple. Now, so if this is adding up to 18, this will be, that would have made that a 7, but then this will have to be 6, 8, 9. So this would have an 8, I see. And if this is 5, 6, 8, that's 19, we need 22 here, which is going to be 6 and 7. So the digit that is used in this box here, out of 8 and 7, is the opposite colour to what has been used here, i.e. it's green. One of those is green. This is a 6 green pair. So purple maybe is where we look, is it? No. Maybe purple in the middle box. Looks like purple has to go either here or here to me. So purple in this box. Has to be in one of 3 positions. It's not bad, but it's not quite good enough. Can I do green in this box? It's really close. It's really close. Everything I'm looking at is sort of a whisker away from giving me the positions of all the greens and the purples. Yeah. Okay. Come on, Simon, think. How do we get further with this? Purple in box 2 is in one of 2 places. Do we know? Maybe this is not what we're meant to do. It's tempting though to think if you can get a few greens and purples on this 22 diagonal, you're really going to restrict it. So if that was purple, that would be interesting, wouldn't it? I mean, even if this was purple, it would be interesting, because that would force a purple here, which would force this to be green. There's all sorts going on with these greens and purples. I think we need to think about this harder. Green and purple are both ruled out from this diagonal because we've found the green and the purple. Green can't be in those squares. Green still seems to be able to be in 4 positions there, which is really very annoying. Is there some way we can improve on that? Thing is, all of these diagonals, I think we've used an awful lot of them now. I've basically used the 17 diagonal. Wow. 7, 8 here, so maybe I've got to come back down here. Those squares have got to be 2, 5 and 6 in some order. We do anything with that? Well, the other thing I've not really thought about is whether any of these are clashing from a disjoint subsets perspective. Whether any of the positions of the putative positions for the greens and the purples. Maybe I've got to think harder about that. Yes! Purple. Purple is there in box 1. It can't also be there in box 5. This is purple. This is purple. Purple's on the diagonal now. So purple is in one of those 2 squares, I think. No, better than that. Purple is here in box 2, which means green is definitely here. So green is getting impacted by purple now. There are 4 purples looking at box 3, so we ought to be able to write in the purple into that square. Now, green. Do we know anything about green? Is in one of 2 places in box 3. Now, I've got to remember, I think, here to check the disjoint sets as well. Green is in one of those positions. So, have we don't actually know. We've got 4 boxes where we don't know the position of the green. No, okay, I'm not seeing how to do that. But look at the 22 diagonal now. If that's green, I know those 2 squares would be 15, because there's a purple and a green on the diagonal. 15, 18, these... Yeah, that's broken. These 4 squares would have to add up to 4. Well, the minimum I could put into those 2 squares would be 1 and 2, which is 3. I can't make those 2 squares both add up to a total of 1. They're going to add up to more than 1, so this square cannot be green. That's green. That's lovely. Therefore, this is green. Therefore, this is not green. That's going to give us this square. That square cannot be a 7 or an 8 now. That's got to be a 6. This square is green. And this square is not, therefore, green. And now, 1, 2, 3, 4, 5. I've done all the greens and all the purples. That is really... It's really gratifying. And this square has to be a 6. And therefore, that square is not a 6. we've now only got one coloured square on this diagonal. Let's just double check the minimum here again. So now we've got 10. That could be a 1, I think. 11. 12. Can't repeat the 1. I've got to be a bit careful because of the disjoint sets, but so those two squares together can be a maximum of or minimum of 3. 10, 11. No, there's still loads of degrees of freedom. Loads. Right, okay. 20 diagonal now. I've got a 7 and 8 pair in here. These two squares have to add to 11 without using 9, 2, 3, 8 or 4, 7. So they're 5 and 6. Six. Okay. So what do we do now? I'm not sure anything's going to surprise me here. This puzzle is seriously interesting and incredibly hard. 1, 3, 4. Oh my goodness, this 6 is in a disjoint relationship with these two 6. This square cannot be a 6. That's got to be a 5. That's got to be a 6. No, I keep looking at these squares and trying to relate them to those two, but they are not in the same position in their boxes. Right, let's come back to this then. That's not a 6 anymore. That's not a 5. There's an aeroplane going overhead extremely low down. Okay, that doesn't seem to have broken the puzzle open, does it? Okay. Or has it? Have we got further from this than I think we might have got? Oh, that's nice. 5 in box 9 is in one of those two cells. So 5 is not here. So actually now look at this box. We've got a 1, 6 pair and we get a 5 at the top. That square can't be a 5 anymore. This is where I'm going to find it very, very easy to miss all sorts of disjoint relationships. 5s. 6s are now in these positions, look. So in any other box, you can't have a 6 in either the middle square or the bottom right square. Now that's interesting for the central square of the grid. Because if I can't put a 6 in here, and I can't, and the reason, just to hammer it home, is if you put a 6 in there, you'd have to put a 6 in both of those squares. They're both in the bottom right cell of their boxes, so that's not allowed under the rules. So there's no 6 here. Now look, we've got 6s placed into one of those two positions in box 5, which places a 6 in box 2. Every digit feels like a triumph, I have to say. Okay, what does that do? Is it doing something here, maybe? There's no 6s into those squares. central cell of the grid is actually quite restricted. It can't be 3, 6, 7, 8 or 9. It's 1, 2, 4 or 5. The square's not 5. Sorry, I know it must be frustrating if you're seeing lots of things before I am. I promise you, I'm trying to give this my very best attention. Okay, what is this telling me? The answer is I don't know. One, 2, 3. These squares here, all of these squares in this box have got to be 1, 2, 3 or 4. Okay. I'm not even sure where to look now. I feel like I should continue to look at 6s, either 6s or 5s. They're the most restricted digits, after obviously the 7s and the 8s. But I think I've done a lot of what I can do with the 7s and the 8s. I'm going to need help with the arithmetic to disambiguate those. So I need to come up with some other way of thinking about this. Can we do anything with disjoint sets? We've got 6s in these positions, which are sort of positions 2, 3 and 7. 2, 3 and 7, that's no use at all. Oh, and I've also got 6s in those positions, so positions 5 and 9 as well. Oh, good grief, right, okay, that's not easy to see, but that's helped me to see it. This diagonal, where do you put 6 on it? You can't put 6 in any of those squares. This square is a 6. Good lord. Okay. That's nice. I get another digit there, that's a 6. Oh, this is big. 6 and 1 into those squares. That's going to do all sorts of things. 1, 1. Let's try and not miss any of the implications of this, because this 6 of course sees this square on the diagonal. That gives me 5s and 6s over there as well. Now R square 6 goes in box 1 by our old friend SUDOKU. It must go here. I might have done all the 6s. Well, I haven't, but I will have done very soon once I put that square in. Now I've got a 2, 5 pair here, so let's get rid of the 2s. From that square... Oh, okay. From that square. That's all you can do. Oh, you can get rid of 4 from that square as well. So I've done the 6s. Let's have a look at 5s, because I got this 5 from that exercise. I can get rid of 5 from this square. There's no 5 on the diagonal now. Look, there's no 5 here because of this 5. Look at column 5 of the grid. I've got a 3 here, ruling a 3 out of that square, creating a 1, 2, 4 triple. This square's the only place a 5 can go in the column. That's a 5. Lovely. That's a 5 at the top. One of those 2 squares is a 5. Oopsie, I didn't mean to do that. Can we get rid of 5 on the diagonal somehow, maybe? Yeah. Yes, we can. Well, we can't get rid of it, but we need to put a 5 on this diagonal. And if you look carefully, it can't go in any of those squares I've just highlighted. So it's either here, where it can't be, or it's there, which must be its home. Do we know... I'm just trying to remember from the 17 diagonal whether we knew... There was only one 5 on it, wasn't there? There was a 1, 2 2s, a 3, that's 4 digits, a 4 and a 5. So we've got the 5. There's no more 5s on the 17 diagonal. Which means that the 5 in box 4 goes here. 5 goes in one of 2 places in box 6. How many 5s have I got now? I've got 7. 2 to place. Okay, well that's still good. That's still good. Now, how do we get further? This square now has to only be 1, 2 or 4 from its box. And 2 is definitely on the diagonal, so this is a 1 or a 4. Similar thing I think is going on. Yeah, this is interesting, this square, because we've got 5, 6, 7, 8 and 9 in those squares. So in theory this is 1, 2, 3 and 4, but we know there's a 2 and a 3 on that diagonal. So that's 1 or 4. I don't think we can colour any relationship between those two. Okay, so what do I do now? 2, 3 and 4. I'm always interested in cells like these two. Now, very good idea in diagonal Sudoku. If you ever get pairs where one of the pairs is on the diagonal, always check the cell that both of them can see. So you can see this square can't be a 1 or a 3 now, because if you try 1 or 3, you'll eliminate that digit from both of those positions because of the diagonal. So this square is a little bit restricted now, because it needs to be 1, 2, 3 and 4 for its box, so it's just 2 or 4. Which isn't quite good enough, is it? At least I don't think it is. I'm not sure, but I don't think it is. So the 3 in box 5 is in one of those two cells. And before I start lamenting my inability to finish this, I do just want to say to Lizzie01, this puzzle is incredibly good. It really is something of a masterpiece. And I desperately want to be able to finish it. 1, 2, 4. I can't see how to do that. 1, 2s and 4s into those squares. Whoopsie, not those pencil marks, those pencil marks. Why were we given these 2 digits? This 4 maybe, that's fixing this box. So let's just check though whether the 4 is eliminating anything disjointly from the sort of right hand cells, these cells of the grid. No, it doesn't look useful. This square can't be a 4, it's the only interesting one. Now, what can that be then? So it can be 1, 2, 3 or 5, I think. No, sorry, I think that's probably, this is probably a waste of time, but let's be diligent. 3 in the bottom middle position. So 3s come out of all of those cells. 3 is not in this square. So this square can only be 1, 2 or 4, I think. because this one can't be 5 or 6 or 7, 8 or 9. 1, 2 or 4. Not sure. Yes, I am sure. I've got something. Right. Look at column 8 now, and ask where 3 can go in the column. We don't quite know, but we know it's not here now because of this 3 thing we just found. 3 can go here or here, one of those 2 squares. Now look, one of these is on the diagonal. So again, is it possible this square is a 3? No, because if this is a 3, you can't put a 3 anywhere now in column 8. But if this isn't a 3, where does the 3 go on the diagonal? There's only one square that can be a 3. It's not this one, for the reasons I just mentioned, it's this one. That's a 3. Let's get rid of the red highlighting. Ah, that's a 1. That's a 1. And 1's in one of 2 places in box 5. It's not here. It's not here. Ah, it's just beautiful. It's beautiful. Where does 1 go on this diagonal now? These 2 ones we've just put in rule out those 2 squares. Every other square is used up apart from the central square, which is now a 1. That's not 1. That's not 1. And 1 on this diagonal now. We need this square to be a 2 or a 4. 3 is locked into one of 2 places in box 1. Come on. One more. Come on, Simon. 1, 1, no. This diagonal needs 2's, 3's and 4's on it, I think. Does that sound right? 2's, 3's and 4's. Now, can we eliminate anything easily from those squares? That's the question. Unfortunately, the answer is I don't know. 1 is not in that square. 4, 2, 3, 4. 4's in one of those squares. 2, 4 pair in the column. I think I already knew about that if I'd thought about it. That square's not a 4. So we've got a 4 in here. We've got... Oh, please, Simon. This is a long video and goodness only knows what's going to happen to the syncing of the voice with the video when I'm recording this on my laptop. Oh no. What am I missing? Let's check the diagonals again. This 2, 4 pair, is there some way I can eliminate? I can see, yeah, hang on. That square can't be a 2 or a 4 now, because if it's either of those, it's eliminating 2 and 4 from the diagonal. Here we go. 1 or 3 into this square. No! I don't believe it. 2, 3, 4 there. Ah, got it. Got it. 2, 3 pair in row 9. Look at the 2, 3 pair in row 9. Look at this square. This square sees both of them. In fact, the 2, 3 pair in row 9 gives me that digit. So I could have done that ages ago. Sorry, but that digit... Doesn't seem to do anything. So let's come back to this, which is what I noticed. 2, 3 pair looking at this square. If this is 2 or 3, bang bang, those come out of those squares. So this square cannot be a 2 or a 3 and is a 4. That gives us a 3 if I trust my pencil marks. 2, 4 pair here means this becomes a 3. That becomes a 2. 2 and 4 on the diagonal. Now, in fact, loads of stuff's going on now. That square's a 3. That square's a 4. This square's a 2. 2 comes out of these squares. 3 comes out of that square, gives us a 4 and a 1. I'm not saying anything. I'm not saying anything until I know that this is... Keep going. 1, 1. I need to put 3 into this row somewhere. It's got to go here. That's got a 4 in the box. This becomes a 2. That should be a 1. This 2 is lovely. 3, 4, 1, 3, 2. This square here needs to be a 3. That's not 3 anymore. This square is a 2 or a 5 to complete the row. This square here is now a 4. This square should be a 2. This 4 fixes the 4 and the 2. How do I finish this then? 2s and 5s look like they're a deadly pattern, and they're not on the diagonals. Oh, one of them's on the 22. Oh, I see. The 22 is going to disambiguate everything. It's going to disambiguate the 7s and the 8s as well. Let me just check this 17 diagonal. 9 and... yeah, you can see it. 9 and 8. That's 17 last time I checked. Oh my goodness. Now look, this 22 diagonal, which has been absolutely useless, apart from, I suppose it ruled out a green 7, 8 from that square, sort of many hours ago. But now I've got 11, 12, 13. I need 9 more on the diagonal. Oh, it's so clever. I need 9 more, so I can't ever use 8 here. This has got to be a 2 and a 7. So we now know, that purple is 7. So I can simply click on it, change them to 7s. I know greens are 8s. I need this to be a 2 to make the diagonal work. Therefore, that's a 2, that's a 5, that's a 5. Click tick. Yes, yes, I'm really pleased with that. I know it's taken a very long time, but my goodness me, that was a brilliant puzzle. It was a brilliant puzzle. Holy moly. Thank you so much for sticking with me and watching it. I hope you had a go. I'd love to know how other people found that. I think it was hard. I really do. I'm not brilliant, as you could tell, and have just watched at disjoint sets, but the number of different ideas in the puzzle, even the simple entry and the way that led to the cleverest thing was this 17. This 17 and the idea that with this diagonal and this diagonal you couldn't have 2 1s on it. That's just brilliant constructing, honestly. Loved it. Really enjoyed it. Thank you so much for watching, and we'll be back later with another edition of Cracking the Cryptic.